Okay, good morning, everyone. We'll do this this morning in English. It's my very big pleasure to introduce you all to Jiyuan. Jiyuan studied his bachelor's degree here at Technion National School, and is now coming to the end of his master's degree. The topic is global optimization for precast concrete fabrication and production using digital twin construction. And so the research is a lot about digital twin construction and a lot about optimization and how they work together. Before I give you the floor, I want to greet people on online. I gather that Jonathan is with us and Simpson's here too. So I hope that you online, you can all hear us. And there are,
I suppose.
yeah.
Can you hear me?
And do you see the slides? Are you sharing? Yes, you are sharing.
Yeah, I can hear you.
Okay, great. Thank you very much. Jiyuan, how are you?
Thank you, Rafael. And thank you so much for coming to my seminar lecture, and also the people from Zoom. Shanatova, guys. And today I will share my research topic, global optimization for precast concrete using digital twin construction. In this research, we are seeing the opportunity to use new managing paradigm, DTC, digital twin construction, to resolve the issue in precast planning. And Professor Rafael Zak is my advisor. So, okay. So today my outline will start with the current practice and challenges in precast planning. And I'll introduce you the global optimization. What is the difference between global optimization and local optimization? And why we recommend global optimization? And how DTC, digital twin construction, can support this scheduling optimization. And demonstrating DTC laboratory setup, comparison between local and global scenario optimization. And this too is my main focus of this research. And in the end, it's results and discussion. So this time-lapse video is from a real construction project in Finland. As you can see here, the construction site, inventory space. From time to time, there's a truck will deliver some pieces to the storage, crane lifting the pieces for worker to assembly. And precast construction, due to this offsite production mode, is recognized for time efficiency and quality control. And its global share is keep increasing, especially in North America and Europe, where the worker shortage is very crucial. But the precast construction have its own problem. Factory for production, on the road delivering, site erection, they are separated, and the planning are also isolated from each other. This table is a interview summary of our project partner in the past. And he shared with us that the precast design will freeze 6 weeks before delivery. Delivery slot negotiation will start 1 month ahead. Final slot confirmation, usually 1 to 2 weeks before delivery. And the negotiation approach is mostly via phone call or email. So we can somehow conclude that in the precast, lack of information sharing across stages, factory to site. Manual planning and planning only focus on individual stages. At each operational space, factory, they don't like frequent mode changes, and site, they don't like this delay. And they usually have conflicts. For example, if factory grouping the pieces only based on the minimum mode changes, then deliver them to the site. Where will the site receive? The site will receive the precast pieces with exactly the same dimensions, and erection work cannot be continued because no project can build the building this way. So to address the issue, the current practice of factory planning, so they're using this early due date rule. In the production line, they sequence the pieces. What is the first pieces they're going to produce? The pieces with earliest due date. And in some very highly automated factory like Elementic, they have this manufacturing execution system, MES system. But this system is widely used in other industry like vehicle manufacturing and electronic manufacturing, but less adopted in construction. But the company, like Element, yes, they have. And the main purpose is to optimize the layout to casting beds, minimize strand waste. The strand is the post-tensioning in the slab. Track the production progresses consistent with design changes. In the literature, since the work, Johnson's work in 1954, researchers have developed many topics in optimization of precast production. They formulate the problem in the topic of flow shop, resource allocation, mode changing, and supply chain management. And they select mainly like total make span, cost as their main target. But they fail to address how to deal with the uncertainty. What if machine breakdown? What if the defects? What if design change? What if due date change? So their study is about how they address this uncertainty issue. So they develop a two-level rescheduling model for precast production, mainly against the due date change. So the structure is simple. First level, they will choose the proper production line to handle this external job. And second, regarding this selected production line, they reschedule all the pieces already assigned to the production line using GA by minimizing the delivery penalties. Another study, they address the same issue, the due date change. Two steps. The first step is due date change and uncertainty generator. They evaluate this due date change uncertainty scenario by these two parameters, due date change magnitude and due date receipt time. The magnitude means, okay, the due date change 2 days early or 3 days after. And the receipt time is, what is the time does the factory manager can notify this change? So based on these two parameters, they generate many due date change cases and then solve them one by one using GA. So this kind of like they pre-trained all the scenarios, and if real world happened this due date change, they quickly match up the closest one and apply to the real world. And now we move to the next stage. Site planning, basically carried out into three main categories. First one, traditional activity-based scheduling, lean method, and structure decomposition idea. First, traditional method, activity-based scheduling, they're using Gantt chart, milestone, critical path method, and they based on fixed duration and dependencies. Lean methods like last planner system, they only release ready, sound activities to the workers, and task time planning define the blocks of the working time to enhance the delivery flow, the working flow of trades. Location-based hierarchical structures, they break down the whole building structure into floors, into zones, into subzones to manage the complexity. Another very interesting study for site erection. So this study, they developed a real-time synchronization system to handle disruption in precast assembly using digital twin. They have 3 layers: material arriving in the buffer, crane lifting the material, 4 workers to assembly, 3 layers, and they divide the time interval into small decision cycle tau. And this tau is typically like 5 to 30 minutes. At the end of each tau, they will collect the new information, update the new information to the digital twin, and they will check if material, all the material are ready, if crane is ready, if all the people are prepared. If everything's satisfied, they continue. They perform the work decided by last decision cycle. If not, they make new decision. And this decision is based on the priority rules, simple priority rules, precedence of the job, similarity of the job, waiting time of the job. There's no real optimization like algorithm behind this system because they need to make quick decision. So to summarize the challenge in precast planning, fragmentation of stages, since the factory, transportation, site erection, they are separated. And weak information flow. The information does flow, but through phone calls, through email, not good flow, weak information flow. static assumption and suboptimal decision-making and less adoption of advanced tool. So to address those issues, what do we need? We need to enhance information sharing with short-term feedback to improve the information flow, global optimization for a global solution searching, and capable with uncertainty disruptions. And we need technology as a container to integrate everything in. So now I'm going to introduce you the digital twin construction, a data-driven approach to managing and controlling project in real time. And it shows great potential to manage situation awareness, support global optimization, enable proactive decision-making. The definition of digital twin. 3 levels. First level. No, it's not. They're not belong to similar, but static model doesn't change. It's static, like BIM model. And digital shadow is one-way dynamic. The virtual model will update when there's any physical changes. And digital twin is like update two-way dynamic. It's interactive. The virtual model will update when there's any physical changes, and also it can analyze the surroundings and make new recommendation decisions for real world. And to guide this interaction, PDCA cycle. This is this structure is according to the principle of continuous improvement. It's very similar to control theory. For example, we are in the situation and we analyze the situation and we make decision to improve or against the situation. So that is basically this structure. So we combine digital twin, we combine PDCA cycle, we somehow arrive at DTC. I'll show this picture larger. Yeah. So the key part of digital twin construction is this. We interpret the data from the construction side, and now we update to the status model. What is a status model? Status model contains the current status of our building, of the worker, maybe of the whole construction site layout. And then we compare it with our design model, what we want to achieve in the end. Usually it's a BIM model. And then we make new decision. We check the conformance, we predict the performance, and we make new decision. And this decision as a guidance to the site, and this is a plan to check continuous improvement loop. And the left-hand side, we continuously store the project data together with some historical data from other projects, and we may using some machine learning algorithm to study the pattern to get to improve the future performance. The concept of DTC was first proposed in 2020, and since then, research has developed key components of DTC, like data schemas monitoring system, and digital twin enabled two-stage model in feed-out construction. And surprisingly, we have some study really implement DTC into real project. This one is from this project. This research is from Canada. The main task of this project is build this cement concrete silos, and they integrate BIM model, GIS, and IoT sensors. This is the brain structure behind the system. So let's quickly define where is the PDCA cycle. They have the plan. The plan represented by the BIM model, and BIM model guide to the site doing the job, and from the monitoring, they interpret the data and they have status model. They compare building information model and status model, and they make new decisions. And this is the cycle. So potential of DTC. It already demonstrates strong capability to integrate planning control across fragmented workflows. And some studies shows DTC's benefits in enhancing project management. And in current optimization, people address isolated stages and lack timely feedback for reaction. Gap number 1, no validation of full scope DTC system. The study I've just showed you, this one only focus on the specific job on site. So it's not a full scope implementation of DTC. So gap number 1, no validation on full scope DTC. Another one, no empirical study to test whether global optimization is useful, is better than local optimization So to address the issue, our research aim, can global optimization support by DTC have a better performance than local optimization in terms of reducing the overall waste? And this study is a part of broader Ministry of Science of Israel funded research project titled Digital Twin Construction Feasibility of an Ultimate Closed Loop Planning Cycle, which aimed to evaluate the overall feasibility of implementing the digital twin system, construction system. So my risk question, first layer, is it feasible to implement global optimization of precast concrete within a fully automated DTC plan to check cycle? And what is the performance between how we compare global optimization strategy and local optimization strategy in terms of reducing waste in precast process? So our target, reducing the waste in the precast workflow. So how we define the waste? The waste in Lean, we call it like non-value adding time. So basically, if there is a wall in the full life cycle of precast workflow, we produce the wall, and while waiting in the factory inventory for delivery, and delivering on the road, and then waiting in the site inventory for erection, and then erect. So at these 5 operational stages, we have several ways: mode changing for production, waiting time, waste. Inventory holding, waiting time, waste. On-site inventory holding, waiting time, waste. And transportation, we define like this. If a truck per trip can carry 10 pieces, but we only carry 5. So another 5 empty space we define as waste. And apartment delay is a waste. And I will specify this definition in detail in next slide. So our overall objective function is defined as minimize the total waste in this precast workflow. So apartment delay cost, we define as the penalty occurring when the completion of apartment exceeded planned schedule. And so if you go really into the literature, and also the people, like how they manage it on the site, they focus on the total duration of the project. And in literature, we call this total make span. So erection delivery time refers to the total completion time. Total penalty for extending total erection time beyond the planned schedule. For example, so what is the difference between these two? For example, I have a project and my target is from day number 10, I need to deliver 5 apartments per 5 days. So this dotted line is my target line. Yellow, no. Green, this green curve is my actual completion rate. So according to erection delay cost, I only care about the total duration of the project. So I care about here. I'm supposed to finish the project at day 30, but I actually finished day 40. So this is my erection delay period. But for apartment delivery delay, we focus on the delivery flow. I need to make sure at every 5-day checking points, my actual completion rate reach the target. So in this case, I didn't reach here. I didn't need to reach here. This 2 is my apartment delivery delay period. That's the difference. So, like I said, if we identify 5 different ways across the total flow. If we only optimize its own, it may reduce the local operational stage flow, but we have more chances to increase waste in other stages. For example, they always have the conflicts like grouping method, I already showed in the very beginning, and storage pressure transfer between 2 storage and dispatching rule. So these 5 operational stages, they have their own conflicts. So that is actually our motivation, why we want to use this global optimization to optimize the overall workflow to make all the operational stages achieve a higher level goal, right? So to test it, our methodology and experiment design. In this research, we adopt a hybrid methodology. We combined physical and computer simulation. The purpose of physical simulation, the proof of concept for full scope DTC system, generates empirical data under controlled conditions. For stage number 2, computer simulation, model calibrate with experimental data from stage number 1, test diverse project scenario and planning strategies. The planning strategies refers to global and local. So you may curious, why don't we test in the real project to test our strategies? The reason is, first, we couldn't really find a company owns a full life cycle, owns everything of a precast project. And also the main reason is, another main reason is construction project is a one-off process. Each building is a one-of a kind. We couldn't rerun the project multiple times, control the starting points to compare our strategies. So actually we have advantages. Both of them are cheaper and faster. We can rerun multiple times, control the starting points. And specifically for stage number 1, in the laboratory setup, it's easier to control the negotiation between machines. And for stage number 2, we can design project scenario freely. The methods, stage number 1, physical simulation, 5 runs for each scenario, local and global. The building size is 2 floors, and each experiment lasts for 4 hours and 4 workers at a time. So the main reason, the reason that we don't run all 8 floors, the full project in the physical simulation is that 2 floors already took us 4 hours, so we couldn't imagine like how 8 hours took us. And computer simulation, multiple runs to test diverse scenarios, 8 floor, and this simulation time is mainly depends on how many plans we choose at the beginning, which I will explain later. Experiment design. We control the starting point of the project first. So same disruption, same insert to the exactly the same project starting time. And then we using 2 strategy to compute in parallel. We compare the performance in the end by production idle time, which refers to the mode changes time, inventory level, truck utilization, and delay. And this project control parameter, how we control this project, I will give an example now. So a project scenario example. Imagine there's a project, a precast residential project, planned for completion in 8 months, requiring the delivery of 6 apartments per month. And this project is highly reliant on a very busy factory. And this factory can only allocate 2 production lines to us. To meet the project schedule, the factory is allowed to start production earlier, but no early than 2 months before erection begins. And the site inventory is very constrained, only 15 pieces. We can start with only 15 precast pieces. So given that project scenario, we control our parameters. The key parameter control, target apartment delivery rate is 6 apartments per month. We're using this target rate to calculate our apartment delay. Number of production line, only 2. Earliest production starting day, minus 60, 2 months. And set inventory limit, 15. Experimental scenario, how the DTC structure can fit into our research. So again, we found the loop. So maybe we're starting from the bottom. Production, delivery, erection, doing the job. And we using monitoring system and scanner to capture the status information through digital twin. We update the information, we feed it into optimizer. And optimizer make new decision, production plan, delivery plan, erection plan. We convert it to digital representation. We give the next cycle of do. So now we will focus on this optimizer. I'll explain you what is the difference between local and global optimization. Local optimization workflow, 3 steps. The first step is site plan enumeration. And then we choosing the best plan N by minimum apartment delay. And then this site plan N becomes my input. We feed into the production delivery optimizer. We receive the production delivery plan and prime according to this local objective. Global optimization workflow. the step number 1 is the same, site plan enumeration. But instead of choosing right after, we feed all the candidate site plan to the factory optimizer. And before step number 3, we receive a integrate site candidates list. And we evaluate its uncertainty. And final step, we choosing the best integrated plan based on this global objective and as well the score from the uncertainty assessment. So despite the structural differences, the main difference is the objective of local and global. I already explained what is the definition of apartment delay, but in local scenario, we're using the piece delay. What is the difference between piece delay and apartment delay? Here, another example. I have a apartment, and this wall is delayed. So according to local scenario, factory and site contract, a delay in one precast wall only occurs a penalty for that single piece. That is local scenario. And global scenario at project level, a delay in one precast wall prevents the entire apartment from being completed, delaying the entire apartment and slab. Without that wall, I cannot install all the select pieces. So that's the main difference between local and global. Site plan enumeration. So now I'm going to explain this step number 1. Site plan enumeration. So this is the picture from the Precast project. As you can see, this at the very beginning of the project. They starting erect the walls in the outer layer due to the rules of wall continuity. Another picture you can see here and here. They finish this apartment first, and then they switch to other zones. Another one, more obvious, they finish this block first, and then they will switch to another block. So until now, we have seen this project they adopt a mixed site plan strategy of wall continuity by blocks, by floors, by zone apartment. So they based on basically they're using the idea of location-based structure. So in our graphic site plan enumeration, we're using the same heuristics, mixed heuristic. Okay, so production factory optimizer. So so this is all example of wall production delivery model, and the objective function I explained many times. So we have 4 decision variables. The first one, assignment of wall to tables. I have a wall, so which production line will handle this wall for production? Credits relationship in a production line, what is the sequence of the wall? And for each wall, production start time and delivery start time. And our mathematical model is subject to 5 constraints. The first, each wall can only assign to one table only. Precedence time continuity for production. So that's how the sequence in the same production line. Only the previous wall finished production, the next wall can start. Delivery after production finish, obviously, and we cannot exceed both inventory limits. So since our problem belongs to the classic of combinatorial problem, and we can formulate as an integer linear programming model. And this model is NP hard. We cannot find the exact solution using solver in the feasible computational time. So most of you can see if you go into literature, most of the people are using GA. It's the most popular algorithm to solve this kind of problem. And we also using GA as our main solver. So this is the GA structure. We read the status information from DTC, and it goes to initial population processing. In initial population strategy, I split into 2. 50% of the initial population will respect factory priorities. Another 50 will respect erection priorities. So in this case, my motivation is that we won't stuck in local optimum because it's trying to find in the middle to balance factory and site. And goes to fitness calculation, calculate the current solution quality, just calculate this objective function. And then we goes to genetic operator, and after each genetic action, we have a repairing mechanism. This repairing mechanism ensures all my child solution is feasible. We can use this solution for working. This is example of how the repairing mechanism make an effect. So you can see V1001, V1013, V1009, they represent wall production job. And the color indicates their dimensions. If two walls have the same dimension, so they don't need a setup between. If two walls have different dimensions, yes, they have a setup to set up the dimensions. So in parent solution, we swap the wall, and we receive this, and we reach the child solution. The system detect, oh, the dimension is different, but you don't have a setup time, so detection infeasible, and we will insert a setup time and push all the jobs forward. Validation of optimization tools. So we designed 7 scenarios. Which those 7 scenarios is like it's not very extreme. It's not very extreme scenario, but we can predict the expectation of the output behaviors. Let's have an example. So scenario number 4, poor flow. So I set very high cost for factory inventory and delivery penalty. I don't recommend wall store in the factory inventory, and I don't recommend any delays. So the expectation behavior of delivery, all the delivery will start once ready, because no walls want to stay in the factory inventory. And we plug all the parameters into the GA, and then we receive the output. Factory inventory remain very, very low level. It's always 0, which means that all the pieces delivered once it's ready, right? And this is a partial solution. As we can see, after production finish and 1 day curing, all the delivery starts, all of them. And we have like 6 more scenarios. So physical simulation, first, evaluate the feasibility. Second, generate empirical data under consistent environmental conditions to validate, to calibrate the computer simulation. Physical experiments setup overview. We have in the lab, we build a 1:25 scale physical model of building, and we have workers and like a foreman, and the monitoring system and the scanners will keep capturing the data from the construction site, update to the SQL database is where we status model, and we compared with our, together with the BIM model, we feed the information into the optimizer, we make new decisions to the next doing cycle and do check. Okay. Physical environment layout. So inventory and our construction workers. This construction site, floor plan, monitoring system, right? 4 cameras. And this is the real-time detection model from the monitoring system. And this scaled building, the real dimension is 2.3 meter long, 0.6 width and this height. And of residential buildings, constructed in Helsinki, Finland, 300 more precast pieces, laser cut wood, and nearly 300. We simulate the concrete. We simulate cast in place concrete using 3D printed plastic. This is a time-lapse video while we were working. The logic is simple. We deliver the pieces before the day start, and workers start piece erection job. If we found any defects, we rerun the optimizer. Then we continue the next phase. If there's no defects, working until the day end. And the computer simulation logic is exactly the same as our physical. The only difference is in the physical experiment, people erect the pieces. But in computer simulation, computer help us to simulate the process of piece erection. Results. So this is the tables, like partial tables from our physical experiment. This table we recorded the time for day start, the time for day end. When do we detect the defective piece, and when does the optimization run for new decisions? And from these two entries, we can know the information that this optimization ran for 5 minutes. Under table, we recorded the timestamps for each erection finish time of each pieces. The raw element status. So this table summarizes for each precast pieces what is the production starting time, what is the delivery starting time, what is the erection finish time. So since we have different type of precast elements, we have bathroom pole, walls, hollow slab, stairs, elevator shaft, and each of them, they have a different time distribution of erection. Now we use this information to calibrate the computer simulation. So to answer the risk question we raised at the beginning, to what extent is it feasible to implement global optimization of precast construction within a fully automated DTC control cycle? So to answer this question, there is a prerequisite question embedded inside. Is a fully automated DTC cycle itself feasible? So to answer this sub-question, we perform a set of experiments within the broader Ministry of Science research topic. The experiment is human planning and control versus machine planning and control using DTC. This is the output. This is the result from the experiment. 5 runs for each, 5 runs for human planning and 5 runs for machine planning. It's too small, so this is better. So the y-axis is the cumulative apartment number erected, and this is time. So we can see the right curve is machine planning, and we perform successfully 10 runs. So we can say that yes, so it is feasible to run fully automated DTC cycle without any human inspection. And surprisingly better, we can see that machine actually have a better performance and more resilience plan than the human. This is their standard deviation, right? So now we can start to answer. Now we can say that a fully automated DTC cycle is feasible. And now we can answer, we can see the question, is it feasible to implement global optimization of precast within a fully automated DTC? The experiment. So this is 5 runs for local scenario using DTC. And we add in the global results. And this the thicker line is the average of global and local. Right. So we compare the mean duration. We can say that global outputs is better than local, and both of them are running successfully. Standard deviation for local is 4.2, for global is 0.8, which indicates that our global plan is better and more stable, more resilient than local to handle uncertainty. Delivery rate, total rate is a total production, like total cycle time, apartment per day. For local is 0.67, for global is 0.86. And this filter rate is this. Okay. So you may notice for both curves, they have two periods. One period is this relative flat period. Another period is this steep period. The reason is that this flat period is occurring when there's a transaction between floors. This is from 0 floor to 1. This is from 1 floor to number 2. So this filter rate calculates what is a steep rate. So we can see global is 0.9 and local is 0.68. Discussion. So first, limitation. So our simulation is only built on one project. So we can't say so. Our finding cannot transfer to other project with a different size and different country, let's say. And simulation limitation, we didn't physically model factory and transportation in our experiment. So the logic may not transparent in the experiment. and limited runs, only 5 for each scenario of physical runs. And our computer simulation is still ongoing. And today, my discussion and contribution will only based on what I have now. Discussion about the feasibility of DTC. I split into 3 layers. First, technical feasibility. So through 2 sets of experiments, human and machine, global and local, we can answer yes. The technical feasibility of DTC, a fully automated DTC is feasible. A global optimization within the fully automated DTC is also as well feasible. And industrial feasibility, what happens if we scaled our setup up? So my answer is yes. Technologies like cameras, monitoring system, RFID are already in factory, already in the industry, like the company like Buildos and Versata, they're already using like AI and computer vision to detect the building progress. And in terms of the resolution of the camera, lab requirements is much higher than the real world. So we can say industrial feasibility is also proved, but the technology shifting needs testing in the real world to calibrate. Commercial feasibility, like in the contract aspect, it's feasible under same company and joint call center for site and factory. So if all the stakeholders along production, transportation, third-party transportation, and direction data belongs to the same company, so they already share the same goal. So we don't need to like worry about that. But if they belongs to a different company, they are not a joint cost center. So a collaborative contract within the shared objective, shared rates, and shared rewards should be addressed before. So another discussion I want to talk about our global optimization. Is our global optimization can find a global optimal solution? So no, not guaranteed. No, not guaranteed. So we can, from this, we can see every production and delivery plan will adapt itself according to each set plan. But the set plan will never adapt itself, optimize itself according to given production and delivery plan. If we allow this two-way interaction, the computational power, the computational complexity will dramatically increase. So because this computational complexity and the quality of solution, the trade-off, so we're using this split structure of optimization. But anyway, we already proved that our current global structure is more stable, better than local. So because this computational complexity, we using this hierarchical structure. So maybe in the future we have the interest to develop a real global algorithm. So conclusions. A fully automated DTC is feasible. Implementation of technologies need testing. We just need to calibrate in the field, and collaborative contract need to be established before the time. And DTC can support global optimization, and from our current result, global optimization delivers better and more stable outcomes. So that is basically what I want to share today. And thank you so much for your time, and also people on Zoom. If you have questions, I'm here to answer.
A little bit of time. So let's see if we have any questions and discussion with you.
Hello, Tanya.
Great work, first of all, thank you. I have one question. So you were talking about scaling up, but you also said that you assume that there are 2 production lines dedicated to your site. It's not necessarily the case. You got to isolate the factory from all other clients, but that's not necessarily the case. I'm wondering, how do you think this global optimization will work if there are more than one construction site?
Right.
Depending
Okay.
on the same factor.
Yeah. So our scope, we focus on the one project, and we assume one factory and one logistics party and one site. This is our assumption, but I can answer your question based on what what I understand. So DDC is a like continuous improvement system. So typical in the factory production, we using this kind of PDCA. We improve a process. A process is a single production line. Finally we want to achieve a higher machine utilization and a higher throughput. But DDC is in the end we want to multi-process. It's many processes achieve a higher level goal in the system. So so maybe this assumption we can adapt your assumption into our algorithm. For example, if we can handle multi-factory because we just need to assume if we have the information, how long you can allocate me, how many production I can allocate for me, and if there's any change, we can adjust our parameter to handle the case of one project, to address the case of one factory, and this factory is supplied to multiple construction sites. And yeah, this case handled. Another case is okay.
That's what I asked.
Okay.
I'm just wondering
Yeah.
if the optimization
So-
is possible.
So currently we need to adjust the parameter because all the parameter we can adjust in real time for each run. Another because you're asking about industrial feasibility. In our simulation experiment and our physical simulation, we have the time limits. We cannot wait this GA run for 24 hours and then make a new decision. But in the industrial in the field, we allow, because it depends on the decision frequency and decision cycle of the real factory. If they will decide their new plan per 2 days, so which means that our algorithm can run for 2 days. I throw all the inputs in, I throw all the information into GA, run for 48 hours, and give me a better solution. So we can adjust this parameter based on your multiple factory. Yes.
Multiple sites.
Multiple sites.
Any questions from our Zoom partners? Sure, we have. Any more questions? Yeah,
Hello.
Maybe I introduce myself. I'm a civil engineer. I manage some construction companies and also manage the construction company that was owned also a precast plant. So first of all, I want to praise your lecture.
Thank you.
Very, very dedicated and very sharp. Thank you very much for the lecture. I saw that you, in the part of the optimization of the cost, you didn't refer to capital cost. You refer to the transaction cost,
Yes.
storage cost, and things like that. Can you explain shortly, first of all, how did you define storage cost? Not the verification cost, because this is obvious, but the storage cost. And second is, why did you omit the capital cost?
Yes. Okay. Wait. Almost there. So I think you mainly ask two questions. Where is the capital cost? Where is the material cost? Where is the labor cost? Right?
When you manufacture early,
yes,
you pay early the capital
cost,
and it takes time until you get the payment.
Yes. So my target is not to compute the cost, even though my objective representation is cost, because all of them they are waste. We are trying to minimize the waste according this precast flow. It's not we use the cost representation. We transfer waste into cost, but we didn't consider that. We didn't think about, like, okay, you asked about capital. If we starting earlier, why we? So okay, so currently we don't have, but in your case we can add this parameter and it won't affect the total structure. We say we can add like, if you starting earlier, you will pay a overhead. You will pay a capital cost of early production. We can simply add it to our GA. It won't affect the overall structure. And I'll explain I'll explain more about this objective function. So this function, it is cost, but it's not actually any related to project cost, labor cost, material cost. We just transfer the waste into a cost representation. This is the first question. And second question, I think you're asking about, can you remind me?
No, you answered because you said you didn't calculate cost, you just calculate the difference between two costs.
Yes.
So it's not, I asked, how did you calculate the
inventory.
Inventory
Yes.
cost or the on-site
Yes.
inventory cost?
Yes. So we have the information. So from the interview, we have the interview with the project manager of this case study. So he shared with us what is the like factory overhead, what is the truck delivery per trip, and what is the apartment delay. We have those costs, but according to you asked specifically inventory costs. So inventory costs, we didn't set any. We just set a bar. If your stock number exceed this bar, I'm not allowed to. So below this bar, because we have the space to storage, why not? So, but in terms of calculate the overall flow, overall waste, we can assign like very, very little cost, like 1, 2. We just calculate how many time waiting time of the whole project pieces.
Maybe I can help with this because the capital costs or the financing costs for the production are reflected by the inventory cost in the factory and on the site. If we had the actual cost, you could say interest rates for capital are 10%, and then according to the time it takes, the longer the piece is produced in advance, the more we have to pay for inventory cost, for capital, for finance. You haven't done that. It's a simplification because we assumed that the cost of preparing the ground in the site for more storage is more than the financing cost if interest rates are low. If interest rates are high, then the finance cost will become much higher. So there is a certain simplification, but it can be built into the factory inventory and the site inventory cost. And then, yeah, I guess that's enough. Let's see.
I add one more remark. I'm not sure that I understood when you run a factory, precast factory, you have one of the goals is to have the work continuation, the workflow, steady workflow, and less
less waste
of the
Idle time, waiting time.
tables,
Table idle time.
Precast molds or whatever. And then I don't know if there is a way to evaluate the difference between early production with the flow of work, and in a multi-project, like I'm taking your question a little bit further. In a multi-project, sometimes it's much more economical to product early, even if you take the capital cost, because you have a steady workflow.
Yeah.
And does your model take into consideration other projects that you can provide the gap for them, and then maybe make your project more efficient?
Okay. So currently we didn't think about one factory handle multiple projects, and how we compare different project priorities. But wait a minute.
I'm sorry.
Yeah, it's fine. I like your question now. Yeah. So first, we allow early production. But early production result in inventory in the system, and we calculate this inventory cost to have a balance of early production and ensure timely delivery. And for multiple projects, I think the idea just occurring in my mind is if we allow a factory produce for multi-project, we need to first evaluate the priorities of the urgency of the project. If a project very urgent for one defective piece for reorder, how we have the mechanism to calculate the priority, maybe reducing one production line for a project and allow this production line can handle this very urgent job. So in this case, yeah. So our system we can have a one parameter cost, which is external production line. So if you said this is very urgent, so you can starting a new production line, handle this job, and not affect already working production line. But there will be a capital cost, penalty cost. And yeah, so we also need to consider that what is the proportion of the cost, because the GA is running, it's optimized based on the priorities of each stages. So we need to carefully think about how to calculate that priority proportion, so can handle your case.
So I guess the conclusion of this part of the discussion is there are some limitations about the parameters that we have not taken into account.
Yeah, also the scope.
And the last suggestion, it's not a question, a suggestion. I think you should look at a way to produce data to make
For control.
For after the fact control, because you have to amalgate this data into the pricing system. And if you look, one of the things that you can do is use this data that you collected after the fact with the pricing system for the next job. So I think you should look at the if you develop a model, that the model should also have a possibility to add a capsule for actual data collection for the pricing for the next job.
You mean we need some real data from the real factory about cost system, about the cost to adapt our.
Well, the other way around.
Then
running a DTC system, over time you can accumulate data and then you can give costs for future jobs more accurately.
For future jobs. Okay. Thank you.
No other questions? So before we finish, I do want to, on your behalf, say thank you to a number of people. Because the research and the setup and all was not just a single person job. It will be said, Jiyuan design